Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Welcome to the Visiting Speaker Series. My name is Tamra Pesek. I'm very pleased you could join us this afternoon. Tim Flannery is a world-renowned scientist and author. He's written books on just a myriad of topics. All of them are fascinating, and all of them are just beautifully done as well. He's on a huge book tour right now for his latest work, The Weathermakers. And I'm so pleased that he could come and stop and chat with us here at Microsoft today. We are the very last stop in the United States before he moves on to the great country of Canada. So I'd like to welcome here today, and just to tell you a little bit more about him, besides being a professor at a university in Adelaide, and he also runs a museum, the Southern Museum of Australia, and basically runs around the world finding amazing anthropological things that nobody else has bothered to write about. So he's written histories of anthropology in the United States that nobody in the United States thought was that fascinating, and yet they're just incredibly well written and incredibly well drawn. So I do hope that you enjoy this presentation this afternoon, and please help me welcome Tim Flannery.
Look, thank you all very much for being here, and could I just begin by saying that it's not often that I get to speak to the people who wrote the programs that allow me to do my work. So it really is sort of special for me to be able to be here and present to you. And I mean that seriously. It's wonderful to be here. What I'm going to be talking about today is climate change, and it's easy for us to forget that climate change results from a pretty simple problem. At base, climate change is simply a manifestation of an air pollution problem. It just so happens that in this case the pollutants are natural elements of the atmosphere, and they also act in ways that fundamentally alter many of the atmosphere's workings. The gases, such as carbon dioxide, are invisible and odourless, so they have managed to sneak under our guard to some extent, and it's only by looking at the manifestations that they cause in our atmosphere that we've really become aware of just how profound they are in terms of altering the world that we know. Now, is that right? Yeah, great stuff, good. This is a composite satellite image of the Earth at night. I just put it up to remind you all that there are now 6.5 billion people living on our planet, and that many of those people live in the world's cities, and that the great majority have access to at least some form of fossil fuel, whether it be for electricity generation or for transport or whatever else. And of course, the waste products of burning all of that fossil fuel are going into a very finite atmosphere. To get a sense of how large the atmosphere is, we need to just conduct a thought experiment and imagine compressing all of that gas that seems so voluminous that sits above our heads into a liquid form. And were we to do that, we'd discover that the atmosphere is about 1/500th the mass of the oceans. So it's a very finite receptacle to be putting large volumes of pollutant into. Most of the lights you see up on the screen there are being supplied by electricity from the burning of coal. It's easy for us to forget that a 19th century technology lays behind our 21st century gadgetry. We burn coal very inefficiently, converting it into energy at a rate of about 30%. And as a result of that burning, as I say, we create a large amount of carbon dioxide. Very good quality coal is at least 92% carbon, and when we burn it, those little carbon atoms combine with larger oxygen atoms to create carbon dioxide. And the overall result is, if you burn a tonne of very high quality coal, you get around about 3.7 tonnes of carbon dioxide. So, and the volume of that waste stream is both obviously the cause of this pollution problem, but also one of the great obstacles in terms of industry trying to deal with that waste product. It's just a very large volume of it that's problematic. I should just say that I don't like that word, the atmosphere, very much. I prefer Alfred Russel Wallace, who was the co-founder of the theory of evolution with Darwin. I prefer his term for the atmosphere. He called it the Great Aerial Ocean. And when I shut my eyes and think of the Great Aerial Ocean, I can imagine the currents above my head that bring us the weather, and the layers in the atmosphere that allow it to operate the way it does. And also remember that the atmosphere itself, while it's not a living organ of our planet, is a manifestation of life. And I guess James Lovelock said this most eloquently. He said, we can think of the atmosphere much like a cat's whisker or a bird's feather, not a living thing itself, but something created ultimately by life. The gases in the atmosphere are held out of balance effectively by the living things on our planet, and we can imagine the atmosphere as being the result really of the exhalations of everything that's ever lived on our planet, and of course, most importantly, the exhalations of all of the things that are alive today on Earth. Just like to turn briefly to the temperature record for our planet. We're dealing here with greenhouse gases that have the capacity to trap heat near the Earth's surface, and so on to the temperature. So it's best to start with temperature as a consideration. You can see here a graph. It's produced by Michael Mann of the University of Virginia and his colleagues. It's called the hockey stick graph for obvious reasons. It has a long handle and a little kind of business end of the hockey stick. The red line that you see there records the average surface temperature of our planet for something like 1,000 years. This has become a very hotly contested graph, and I'm sure some of you will have caught up with some of the literature, scientific literature dealing with this. Suffice to say here that I don't want to go into that debate in any great detail, but more recent studies suggest that the graph should be perhaps just deflected downwards a little bit with a few more wiggles on it. This version of the graph was published by the Intergovernmental Panel on Climate Change, which is the world's most authoritative group of climatologists, about 400 specialists in that group. So I use this one in preference, at least for the time being, until I update it. Of course, we didn't have a worldwide thermometer grid 1,000 years ago, so our estimates of temperature there are based on proxies, isotopes of oxygen, for example, tree ring data, fossils. But nevertheless, the record is highly consistent with what we know of global climate changes through time. By about 1850, around about here, there was a worldwide thermometer grid. The amount of uncertainty goes down, as you can tell from those grey error bars around the red line, and the grid, the temperature starts taking a little bit of a upwards twist. We'll come back to that upwards twist a little bit later in the talk, but through the 20th century, the Earth's average temperature rose by about 0.63 of a degree. Prior to the Industrial Revolution, average surface temperature of the planet was around about 13.7 degrees Celsius, so quite a cool planet overall. The business end of the hockey stick, those projections, are the things that really captured attention when this graph was first published. And they're a result of a complex analyses using what are called global circulation models, as well as economic inputs and whatever else, and show where the surface temperature of the planet may be by 2100. The lowest of those projections suggest a warming of the surface of the planet by about 1.4 degrees Celsius. The high end is about 5.8. The middle of the range is 3 to 3.5 degrees Celsius, and we'll return to that a bit later on as well. This graph just shows you a somewhat longer temperature record and carbon dioxide record for our planet, this time stretching back 160,000 years. And what you see there is obviously more variability, and that variability has been driven by what are called the Milankovitch cycles, the great celestial cycles that have controlled our planet's climate for many millions of years, and for at least the last million years have brought ice ages and warm periods in a cyclic manner. You can see here high temperatures, a warm period, back down here ice ages or glacial maxima. This temperature record most of that data is derived from ice core studies, so people now have ice cores going back the best part of 1 million years in the Antarctic, revealing these same patterns. And we can derive the CO2 record, this one here, directly from the ice. Small bubbles of air are trapped in the ice, and we can just measure the atmospheric composition back now 1 million years. The Milankovitch cycles describe the way that the Earth circles the Sun, revolves around the Sun, the way the Earth tilts on its axis and wobbles on its axis, and those factors obviously distribute sunlight differently on our globe and vary to a very small extent the total amount of sunlight hitting our planet. But it's those variations that bring us ice ages and warm periods. Don't mistake the CO2 record being so congruent with the temperature record here as meaning that greenhouse gases are driving this change. They're not. What we're seeing here is the great celestial cycles, the Milankovitch cycles, as they vary temperature of our planet and carbon dioxide and other atmospheric gases respond. This end of the graph really is where we see the greenhouse gases taking over from the Milankovitch cycles. We know, because these celestial cycles are highly predictable, we know how the planet should be responding to them at the moment. We should be seeing a cooling trend that would have begun about 8,000 years ago. Instead, we've seen this stability that you saw on the Michael Mann graph, at least part of it, and then this little upward shift in temperature. So these are things that are, the temperature now of the Earth is going in the opposite direction to what would be happening were the celestial cycles still in control of Earth's climate system. It's this part of the CO2 graph that is most concerning scientists today who try to project how the Earth's climate system will respond in future. You see here the absolute maximum CO2 levels now back 1 million years. For the planet, CO2's never risen above 300 parts per million for the last 1 million years. When I was born in 1956, CO2 levels were about here, 310 or 315 parts per million. They're now above 380 parts per million. The lowest possible stabilisation level is around 450 parts per million, although that is looking increasingly ambitious. And business as usual, so if we don't address this climate change issue and the air pollution problem that's driving it, CO2 levels will peak somewhere in that range by the end of the century. Where's all of the carbon dioxide, where's all the carbon dioxide coming from? As I mentioned, we burn a lot of coal on Earth today to drive our electricity systems, and it really is fundamentally a 19th century technology that's used. Brown coal is by far the most polluting of all of the fuels. Thankfully, you don't have a lot of brown coal here in the USA. We have large volumes of it in Australia, and the world's most polluting power plant is located in southern Australia. It uses brown coal. The reason that brown coal is so bad is that it's a very wet fuel, and you have to burn some coal just to dry out the brown coal you want to feed into your furnaces. So there's losses all the way through the system. Black coal, as I mentioned, is also highly polluting, being mostly carbon. When we get to natural gas, there's a fair bit of hydrogen and less carbon in the mix, so gas is the least polluting of the fossil fuels and is widely thought of as a transitional fuel to a non-renewable, to a more low emissions future. And then again, there's lots of other ways of generating electricity, in fact generating power. Electricity is a generic product. You can use the wind, nuclear energy, geothermal energy, photovoltaics, a number of other technologies to generate electricity. And what this suggests to me is that as we as a civilization move towards implementing the polluter pays principle, which we'll have to do if we want to avoid some of the changes that you'll see in future, we'll see increasing competition across the stationary energy sector. So wind is already quite competitive, but soon, and so is nuclear, soon photovoltaics and geothermal and other means of generating power will be in that same level of competitiveness. And I suspect that the sort of changes that the internet brought to information technology and to the media we'll see replicated in the energy sector. At the moment, the transport fuels and stationary fuels are quite segregated. That simply isn't going to be the case in future. You can just think about electric cars, you know. There's one way of that crossover occurring. There's going to be many, many other ways of that happening in future. And of course, all of these sectors will come into greater competition. And we'll return later to some of the implications of those shifts. It's important to understand that the atmosphere is also a truly telekinetic organ of our planet. It's organised internally through pressure waves and layers within the atmosphere, and they can respond abruptly to the forcing brought about by warming of our planet. So greenhouse gas accumulation in the atmosphere is gradual. The warming trend, therefore, is gradual. But every now and again, the climate system readjusts itself to the pressure or the forcing brought about by that warming trend. You can think about the way the atmosphere works pretty much like putting your finger on a light switch. You can add pressure to the light switch and nothing will happen for a while, but then it flips from one steady, stable state to the next. Climatologists call years or periods when the climate system rapidly readjusts to those forcing pressures as magic gate years. I just put this slide up to let you know that people noticed that the weather was strange in 1976. Looking back on it, we now recognise 1976 as one of those magic gate years, one of the years when the world's climate system reorganised itself. And I'll just take you through a few examples of what happened in that year. The examples I have here are from Australia, and that's just because that's where I live. I understand these examples well and I can stand by them, but there are many, many examples from around the world that could have been chosen. I'd like to look at rainfall just briefly. This graph shows annual stream flow into Perth's water supply dams. Perth is Australia's western city, westernmost city. It's a city obsessed with water because there's desert to the north and ocean to the south. It's in a little wet corner of the continent. And you see here that although rainfall varied considerably for year to year between 1911, when records commenced, and 1976, on average, the city received about 340 gigalitres of stream flow into its catchments per annum. Following 1976, there was a halving in stream flow into those catchments, and of course that caused the city great problems. You can imagine what a halving of your income might mean, or halving of business for any industry. What actually happened in terms of the atmospheric reorganisation that led to this 50% decrease in stream flow was of a much smaller scale. Essentially, the Hadley cell circulation that brings those rain-bearing depressions to southern Australia during the winter altered in such a way as to drive the rain-bearing depressions about 100 to 150 kilometres southwards. And that resulted in about a 10 to a 15% decrease in overall rainfall in Perth's catchments. But the rain began to fall in such a way, in such events, and at seasons of the year that cumulatively had a very large impact on stream flow. So as the rain falls during the warmer part of the year, there's more evaporation, soil temperatures are higher, less water gets into the catchments. So those sort of changes amplified an initial small rainfall change into a very large impact on the area's streams. The little red line there just marks the second magic gate year, 1998 to the present. Not so well understood because not as much time has elapsed since 1998. But you can see for Perth at least there that after 1998 the city was only receiving a third as much water, roughly, as it was receiving prior to these changes. Just like to look at the situation for Australia as a whole over a longer period of time. I tried very hard to find a map like this for North America, but the Meteorological Bureau here doesn't produce a lot of data that's amenable to sort of easy analysis by those interested in climate change, which I'm sure is accidental, but nevertheless I'm stuck with Australian examples. What we see here is a sort of summary of rainfall changes across the continent for the period 1950 to 2003. The blue areas here have received an increase of 50 millimetres per decade over that period, so about 10 inches overall, which is quite a lot. The red areas have received a decrease in rainfall of an equivalent amount over that same time period. Perth, by the way, is located down here in the southwestern corner. Some of this is easily explicable just as a result of the warming of our planet. The tropical monsoon systems are bringing more rainfall, particularly in the form of tropical cyclones to the northwest, as you'd expect from a warming planet. And as we have seen, the winter rainfall zones are attracting from this part of the country. These large deficit areas here, though, have a much more interesting origin. They, it now transpires, result from increasing sea surface temperatures in the Pacific Ocean. And those increasing ocean temperatures have altered the atmospheric circulation pattern across this region of the planet in such a way as to change what's the Southern Oscillation. Now, the Southern Oscillation is the weather pattern that brings drought and flood to Australia. So the El Niño phase of the cycle is the dry phase, the La Niña phase is the wet phase. Climatologists refer now to our current weather patterns not as really true El Niño patterns, but pseudo-El Niño patterns, because they do differ in important respects from what we've seen in the 200 years up to this point in time. But nevertheless, their impacts on Australia are broadly similar to what El Niño and La Niña brought. What we've seen in eastern Australia is a prolongation of the drought phase of the cycle. So our droughts are now longer than ever before. Statistically speaking, they're the sort of length that you might expect every few thousand years, rather than having back-to-back long droughts. And the La Niña phase of the cycle, the flood phase, is becoming very attenuated. Computer modelling using global circulation models indicates that as the temperature of the Pacific Ocean increases, these changes will become first semi-permanent and then permanent across eastern Australia. So we'll have a permanent El Niño-like phase of the cycle dominating this part of the country. Of course, that's of great concern to the 20 million people who live in Australia, the majority of whom live in this part of the country here. There's been many profound impacts. So I just point out here that there is not a major city in Australia that's not suffering some form of water crisis at present. In the worst cases, water has had to be freighted in by freight train to save inland cities, and these are cities of tens of thousands of people. In other cases, we have water police now driving about looking for such un-Australian behaviours as people washing their cars or watering their garden, which is a bit of a shock to many people. Anyway, this is just one example of rainfall change around the world. Sub-Saharan Africa offers another fine example. The sort of problems we're seeing in Darfur have at their base, originate at their base in increasing ocean temperatures in the Pacific, in the Indian Ocean. Western North America again offers some examples of these sort of changes, these same sort of changes. I just say briefly that as the planet warms, of course, we will see more rainfall because a warm atmosphere can hold more water vapour. So for every degree Celsius of warming of the atmosphere, we'll see approximately a 1 degree increase in overall rainfall on the planet. It's just the rain isn't falling at the same times or in the same places as it did previously. And of course, what's that, 1 degree for 1% approximately? Yeah, that's the ratio. Yeah. So, where was I? I'll come back to the rainfall in a moment. I'd like to just follow through some of the other implications of a warming Pacific Ocean because they have been quite profound. What you're seeing here is a coral reef that's died of bleaching. What happens to a coral reef as it bleaches is that the little coral organism that grows the reef ejects the crucial partner in its life, and that partner is an algae that lives in the body of that coral polyp and gives it its colour. So the reason reefs are so brightly coloured are the algae living in the cells of those coral polyps. As oceans increase in temperature, the algae find themselves unable to photosynthesise as efficiently as previously, and somehow the coral polyp picks this up. The coral polyp's sensitive to it because the polyp derives much of its food from the products of photosynthesis that the algae generates for it. And I guess it's like a bad business partnership. The polyp gets to a point where it finds the returns just aren't worth it and it ejects the algae from its body. This probably evolved as an emergency response for corals in tide pools, you know, where you go through, say, several hours of high temperature. But in a warming ocean, these warm conditions and adverse conditions can last for weeks or months, and if they go longer than about 6 weeks, the coral simply die of starvation. And here you see a coral reef that's newly been killed. It will, over a few months, break down due to wave surge and just be covered in a green slime. And it's very bad news for the planet, partly because about 1/4 of all marine organisms spend at least some part of their life cycle associated with coral reefs. Partly also because there's 5 nations on our planet that are totally dependent upon coral reefs. And to destroy those... Did such things happen at Microsoft? Surely not. Sorry. Anyway, should I just cancel? Oh, goodness. Oh well. Sorry about that. Hopefully it'll go away. No. Anyway. Yeah. And also, it's just worth remembering that coral reefs produce about, thank you. Coral reefs produce about $30 billion worth of income for people around the world. Many of those people don't have other access to the money economy, so this sort of events have very large impacts across the globe. I'd like to look at the incidence of coral reef bleaching over the last 130 years. Prior to 1950, which is when the first biological manifestations of climate change became evident, bleaching was a relatively rare event. After that, it's become much more common. You can see there's quite an increasing trend here. In 1997-98, between about 15 and 20% of the world's coral reefs were either killed outright or severely damaged by bleaching. So it's a very big global impact. In terms of the Great Barrier Reef, which is the reef I know best, since then it's been a tale of just ongoing bleaching events. 2002 was another very severe event that killed outright or damaged up to 60% of the Great Barrier Reef. This year looked like it was going to be another horrendous year, but then we got Cyclone Larry, and you may have heard of Cyclone Larry here, which is Category 5 cyclone that hit northeastern Australia. It sucked enough heat out of the ocean surrounding the Great Barrier Reef to spare it another bleaching event. So there was sort of some silver lining in that particular cloud. We've already seen the first biological extinctions as a result of climate change. This animal is a creature called the golden toad. It lived in rainforests in mountainous parts of Costa Rica. In 1987, biologists noticed that there was a failure of recruitment in the population. So the ponds that the toads were breeding in dried out, and there was no young managed to survive that year. The following year, biologists went back. They were relatively unconcerned because this creature had only been discovered in 1966. They went back the following year, found a single male toad only in the whole of the distribution of the creature. Again, thought, well, maybe this is part of the normal cycle. It's not too worrisome. Went back the following year and found that male toad again as the sole living individual, and that was the last time the species was seen. It had a bizarre lifestyle, incidentally. It spent 49 weeks of the year underground, and when they came up for their 3-week toad orgy, the males were pretty vigorous and would congregate around these pools the females had come to lay their eggs in. And you see they're very bright orange, so they were an obvious feature of the environment during those 3 weeks. The reason we know this creature became extinct as a result of climate change is that its entire distribution was in an area that was extremely well studied biologically, and there was a meteorological station in the vicinity of where it was last recorded. So we have virtually hour by hour climate record for what happened through that period, and of course biologists were looking as well. 12 years after its extinction, biologists finally felt confident enough to publish a paper in Science explaining what happened, and they were able to discern that the causal sequence of events was as follows: that increasing temperatures in the Pacific Ocean had led to changes in atmospheric circulation that resulted in the cloud cover that sat against these mountains during that critical 3 weeks when the toad was out and breeding, had elevated about 400 to 500 metres higher. And it was that cloud that, by sitting against the mountain, was bringing the moisture that was needed by the species when during its breeding season. And so the clouds were still providing, were still blocking sunlight, but they weren't providing moisture. And it was a result of that moisture deficit that this species became extinct. Now, a lot of people say, oh, so what, just one species? The fact of the matter is that species as distinct as this take a very long time to evolve. And to see them go extinct in our lifetimes is something that tends to concern biologists. You see a winking out of species around the world now, not all as well studied as this, but many of them increasingly, many of these extinctions increasingly being tied to climate change. The latest amphibian assessment report, which was published last year, suggests that a third of the world's amphibians are either already extinct or critically endangered. And increasingly we're seeing studies linking those extinctions to climate change. The most important of those studies came out only last week, linking the extinction of 110 species in a single genus in South America to increasing nighttime temperatures and decreasing daytime temperatures that led to runaway disease problems in those species. So the science is getting better around the biological impacts on amphibians at least. Just like to have a look at mountain biodiversity worldwide. This is just a single example from the mountains of northeastern Australia. It should be no surprise to you that that low mountains have lots of biodiversity on them, and that's because biodiversity takes a long time to evolve and mountains don't last forever. So low mountains are old mountains, they have lots of species on them. These mountains in northeast Queensland here have probably 10,000 species just unique to them, and those species are mostly on the cool summits. They're relict species that live, that were once widespread in Australia but today only survive in these relict mountain patches. This little possum here, I've found fossils very similar to its bones in 10 million year old deposits in Central Australia. They date from a time when Australia was cooler and further south than it is today. We'll have a look at some very simple science that projects what will happen to these species as our planet warms. 1 degree of warming will eliminate about 50% of the species' habitat, but 3.5 degrees of warming will totally eliminate it. And what's true for that species is true for every one of those organisms that live in these high mountain rainforests in northeast Queensland. And this is, again, just one example from one small continent. It's as well to remember that this is the average temperature that is projected for our planet by the end of the century. So you can see the sort of concern biologists have for these changes now that are occurring in these natural systems. Some habitats are likely to disappear altogether as a result of climate change. This is the Succulent Karoo. It's the world's most diverse desert flora. And as you can see, lots of pretty flowers in it. I'm sure that someone's got a garden here that has some species from the Succulent Karoo growing in it. 2,500 species of plants. It's dependent entirely on that same winter rainfall zone that's declining across southern Australia. As our planet warms, that winter rainfall zone is going to retract south. Projections are that by 2050 the Succulent Karoo will simply cease to exist. It's one of the most vulnerable biomes on the planet to this warming trend. It simply has nowhere to migrate southwards to track that winter rainfall zone. It's backed up against the Cape Fold Mountains, whose geology is just unsuitable for such plants to grow in. I should spend a little bit of time dealing with human societies and the impact that climate change will have on us. There's 3 examples here of stresses placed on our energy infrastructure as a result of climate change. In 2003, Europe had an exceptionally hot summer, and river levels fell so low that the nuclear reactors, which were normally cooled directly from river water, had to undergo emergency cooling because the rivers had fallen so low that the intake pipes were exposed, were no longer able to access water. I needn't mention the US Gulf hurricane season in 2005, extraordinary damage done there. I guess you all know that even the pipelines 90 metres below the surface of the ocean were torn up, causing billions of dollars worth of infrastructure damage. Exceptional monsoon in Bombay, again causing infrastructure damage to a gas field in that area. I'd like to talk briefly about changes at the poles. In 2001, when the Intergovernmental Panel on Climate Change's third assessment report came out, the estimates as to how the sea level of, the ocean level may change as a result of this warming trend were very, very limited. People thought perhaps a few tens of centimetres, perhaps at worst case a metre over this century of sea level rise. Subsequent to that publication of that report, a number of events have occurred at the poles that have caused some very serious questioning and some revision of that data. What we see here is the Larsen B ice shelf. It broke up in 2 phases, 1995 and 2002, and broke up very unexpectedly. There's a few things that really should concern us about this. I mean, beautiful, bright ice is wonderful stuff for cooling our planet. 90% of the sunlight that strikes that ice will be reflected into space without warming our planet. When we replace that ice with dark oceans, at least at midday, 90% of the heat energy that strikes the ocean is absorbed and, of the sunlight that strikes the ocean is absorbed and turned into heat energy. The reason that Larsen B broke up was that the ocean, the Weddell deep waters here, had increased in temperature by just a fraction of a degree. They're still cool and cold enough to kill you if you fall into them very, very quickly. But that warming was enough to start really eating the ice shelf away from underneath, really propagating cracks and crevices through it in such a way that it broke up extremely rapidly when it finally did destabilise. The sediments underlying that ice shelf reveal that the Larsen B ice shelf had been stable and in place for at least the last 12,000 years. So again, its breakup is an unusual event, something we're seeing in our lifetime that hasn't happened previously. What surprised scientists the most about the breakup was the response of the glaciers flowing into the Larsen B ice shelf. Of course, if an ice shelf breaks up, it won't affect overall sea level, just like an ice cube in a glass of water. If it melts, it doesn't increase the level of the sea. But land ice flowing into the oceans can have a big impact on sea level. Once Larsen B broke up, the glaciers flowing into that ice shelf sped up enormously. It was as if the ice shelf was acting as a dam, holding back all of that glacial ice onto the land. Following the breakup, there was a great speeding up and more ice going into the oceans. The total impact of Larsen B in terms of sea level is probably only measured in a few tenths of millimetres. But the sort of changes in the heat balance of the Antarctic Peninsula that its breakup caused will have bigger consequences. Down here on the Antarctic Peninsula is a much larger ice sheet called the Amundsen Ice Plain. In 2004, scientists discovered that it was showing signs of breakup. They predicted that within the next 3 to 5 years we'll know whether it's in full breakup mode or not. It's large enough, if it should break up, to raise sea levels with all the glacial ice it holds back by about 1.3 metres. So these are very large-scale changes. Looking back at Earth's climate history, we know that the last time the Earth was as warm as it's projected to be by the middle of this century, sea levels were about 4 metres higher than they are today. So there is increasing evidence to suggest that sea level as it exists now will start changing rapidly through this century, and I believe that will gravely imperil our global civilization. Again, people just forget that our civilization is held together by sea trade. That's what knits us all together. Rapidly rising sea levels endanger that sea trade simply because it's difficult to keep port facilities open. And one of the greatest difficulties comes about because we just don't know how much the sea will rise. People like James Hansen, one of the leading scientists in this area, believe that ultimately we may trigger a rise in sea level of 25 metres. There's enough ice on planet Earth to raise sea level by 70 metres. But projections for this century are certainly increasingly in the order of, say, 1 to 3 metres, perhaps some people even saying 6 metres for this century or century and a half. So they are very large and disruptive rises in sea level indeed. I'd just like to summarise a number of phenomena that climate scientists have linked to the 0.63 Celsius degree of warming the planet's experienced over the 20th century. We've had this severe ENSO event and changes to the ENSO cycle. We've had drought in various parts of the world, breakup of ice shelves, hurricanes appearing in areas that they haven't appeared in before, and increasing severity in hurricanes worldwide. I should just point out that over the last 30 years, the total energy budget expended by hurricanes globally has increased by about 60%. And that's simply because if you want to run a really strong hurricane, you've got to have high sea surface temperatures and lots of water vapour, which is hurricane fuel effectively. So some disturbing trends there. More extreme weather events in the form of heat waves. I was surprised to learn that heat waves were more deadly than hurricanes. They're dangerous to older people and young people simply because they're not as capable of thermoregulating as people in the middle of their life are. That warm European summer that caused problem for nuclear reactors also killed 36,000 elderly people, mostly in France, as I said, and other issues related there to extreme weather events. It's broadly, the science, what we understand about climate change broadly indicates that as we warm our planet, we will reach a point where a runaway warming effect will be triggered. And this is because Earth's climate system seems to abound with positive feedback loops and have relatively few negative feedback loops. The point that many scientists are concerned about is about 450 parts per million CO2 in the atmosphere, which will equate to around about 2 degrees Celsius of warming. The sort of events that they're concerned will occur at that point include the loss of the North Polar ice cap. The latest projections, by the way, indicate that that will occur sooner than 450 parts per million, sometime perhaps between 2020 and 2100. Loss of biodiversity in all natural areas, and that's because species just can't migrate to track their zone of thermal comfort anymore. The largest national park on our planet is Kruger National Park, which is about the size of Israel. Studies suggest that with 2 degrees of warming, it'll lose 60% of its species. So it's a big national park. And I must say I feel that personally very deeply, because I've spent most of my life trying to preserve biodiversity and work towards the creation of national parks. And I now know that unless we deal with this issue of climate change, I will have done nothing but just create death traps for species that simply can't migrate across the planet. I should just point out here too that if the species often need to migrate a long way. When our planet came out of the Ice Age 15,000 years ago, temperatures increased by about 5 degrees Celsius over 7,000 years. And as a result of that shift, the trees that now that were growing in northern Florida migrated all the way to Canada. We're looking at a 3 or 3.5 degree warming on average over a century. So large scale but extremely swift phase of climate change. We've already talked about mountain rainforests, alpine zones. Coral reefs, at least as where they exist today, certainly won't be there with 2 degrees of warming. We'll lose about 90% of the world's coral reefs. Catastrophic phase shifts in climate become increasingly likely. Perhaps we can talk about some of those a bit later on during question time. But these are things like the shutdown of the Gulf Stream. And as I've already discussed, large sea level rises. We can put together a budget, a carbon budget, which gives us a sense of how long we've got to act before we reach 450 parts per million CO2 in the atmosphere. We've already put about 283 gigatons of carbon into the atmosphere since the Industrial Revolution. And I should just point out there too that the rate of accumulation of carbon in the atmosphere is obviously increasing. And that's because we're just producing more and more energy, most of it from fossil fuels. Half of the energy generated since the beginning of the Industrial Revolution has been generated in the last 20 years. So, increasing rate of accumulation in the atmosphere. By 2020, we will have used more than half the carbon budget. In other words, we will have emitted more than half the CO2 required to bring us to 450 parts per million. And by 2040, we are totally, well, pretty much totally out of budget. And I put this up really just to reinforce the point that early action is the only course of action, because we can't change our energy systems overnight. The average age of a motor vehicle in the United States is about, well, not the average lifespan of a vehicle here is about 13 years. The average lifespan of a power plant is about 50 years. So these things change relatively slowly. Where will the savings be found? The International Energy Agency put this little pie chart together. I don't think it's necessarily the best indication, but it's some indication at least. The IEA thinks that end-use efficiency gains is where we're going to find the lion's share of the emission savings. That means, energy-efficient light globes, selling your SUV and buying a hybrid fuel car, which cuts your emissions by 70%, transport emissions by 70%, those sort of things. They think another 20% will come from renewables, increased renewables in power generation, so more wind, more solar, another 10% from nuclear power, and 13% from changing the way we use fossil fuels.
Sorry, one quick question.
Yeah, sure.
Switch to a hybrid vehicle, would that be charged against the 7% or against the end-use efficiency?
End-use efficiency gains, I think.
Oh, it would be?
I think so. I believe so. I think so. I should check with IEA about that, but
that's fine.
Yeah, it certainly gives you an increase in efficiency. But you could
give it as an alternative fuel would be the other way to gauge it. That's all right.
It's sort of, I guess it's not. You've got an electric motor, but it's the fuel for it's still coming from the fossil fuel. It's just being captured and reused in a more efficient way. I just put this up to show you the North Polar ice cap, which is probably if you want to see evidence from space, I mean large-scale evidence of the impacts of greenhouse gases on our atmosphere, this is where you'd go to see it. There's been a large retraction, about 20% in all of the polar ice cap in the last quarter of a century. And what you can't see there is that how much the ice has thinned.
I was just going to say, what about factoring in the savings from not having to go around Cape Horn or through the Panama Canal? Because finally, I'm just looking at your map, the Northwest Passage is open.
That's right. Northwest Passage will be open. It will be. Whether there'll be still ports at either end of it that will remain serviceable by the end of the century is a big question. Probably the big question. And we see Greenland there with its ice cap, the last remnant really of the great northern polar ice cap that the mammoths would have recognised. There's increasing evidence of alarming rates of melting around the margins. Should all of that ice melt, and it's unlikely to happen in the next several centuries, but should it all melt, there's enough water frozen in that ice cap to raise global sea levels by between 6 and 7 metres. So again, there's still some large impacts in the northern hemisphere to be realised. I used to think about this problem, I guess, as an environmental problem or a technological problem or an economic problem. I now think of it much more as a moral problem, and the reason I think that is because the problem results from the emissions that we all make, the CO2 emissions that we all make as we just go about leading our everyday lives. It's not someone else or some evil industry or anything else. It's actually just us driving our cars, using our electricity and doing whatever else we do. And I found that a sobering thought, but also a very liberating thought, because it leaves a lot of room for individual action. And I think that's, at least for me, it's been a very rewarding thing, just trying to come to terms with this personally as much as politically and in other ways. So I think I'll leave the talk there and open the floor to questions. Thank you very much. Yes.
In one of your earlier graphs, you showed the CO2 emissions and different ways of generating electricity. And you indicated that there is actually CO2 emissions with solar thermal and wind, which surprised me.
That's because at the moment we have to manufacture that infrastructure using the fossil fuel-driven economy. So, yeah. Yes.
You mentioned changes in the Gulf Stream. Can you talk about that?
Yes, look, we know that in times past, as ice has melted across the North Pole, that freshwater fluxes into the North Atlantic have disrupted the Gulf Stream. And the Gulf Stream's hugely important for Europe and North America because about a third of the heat that they enjoy comes from up the Gulf Stream in that warm water. You know, water's is 770 times, I think, more dense than air. Therefore, one cubic metre of water warms 3,000 cubic metres of air. So, should that shut down, Paris would find itself with a temperature more like that of Siberia than the temperature it enjoys today. The Greenland ice cap record reveals that those changes happen very swiftly. They happen over a couple of years to a decade. So it is one of those things that scientists are looking at to try to determine how likely this is going to be. The people at the Hadley Centre for Climate Change Research think that the likelihood of this happening this century is in the order of 5%, which is low. But you know, that secret Pentagon report, I don't know whether you caught up with that. The Pentagon commissioned a report on the potential impacts of the shutting down of the Gulf Stream, which suggested that there'd be such huge migration of people and such impacts on economy as to destabilise our global civilisation and lead to war and all sorts of strife. So a low probability perhaps, but with high impacts should it occur. I should just say actual measurements of the Gulf Stream are hard to make. It's got so many little eddies and curlicues. You know, the changes in its flow at the moment are just about at the margins of our capacity to detect. They're on the order of 1 or 2 Sverdrups, and Sverdrup's about as much water as the Amazon puts into the ocean a year. So, but the return flow of the Gulf Stream does seem to be slowing appreciably. So it's an area of great scientific uncertainty, but something I think that people need to keep their eye on.
How alarmed is the Australian government these days with climate change?
I'm sorry, could you repeat?
How alarmed is the Australian government with climate change? Or is there a lot of action going on? Or?
Oh, the Australian government believes that coal is the future. No, there's no alarm whatever. In fact, until late this year, they've been in deep denial about climate change. They're now, there's only 4 nations on Earth that have not ratified the Kyoto Protocol: Australia, the US, Monaco and Liechtenstein. So it's an interesting sort of coalition of the unequal or something. But no, Australia's really lagging badly behind, as is the US. Now, when you go to Europe, you see some extraordinary investments in the development of this new energy infrastructure that will drive tremendous wealth in future, I think. But Australia and the US both believe fossil fuels are the future. So this, yeah.
Have you come across any data that indicates, if we stop burning fossil fuels tomorrow, how long would it take for the climate to return to its normal cycle?
Well, there's a lot of inertia in these systems, and the CO2 that we release today as we drive our cars home or keep these lights going, and I presume maybe you've got a fair bit of hydro here. I don't know. I don't want to be too hard on people in this day. But that CO2 will last for about a century in the atmosphere, and there's a heat transfer into the oceans typically takes about 3 decades to equalise. So the suggestion is that if we stopped emitting tomorrow, we would take a century and a century and a half to stabilise climate. Nevertheless, worth doing, because if you don't do it, you just keep adding to the problem. Probably the Montreal Protocol to dealing with CFCs gives you a sense of how things may play out if we do limit emissions. That agreement was realised in 1987, and it's only last year that we've started to see a significant decrease in the size of the ozone hole. But, these things do take time.
Part of that inertia is the planning for new power development, and I see China obviously being one of the big concerns. Is that factored into some of the targets that you're coming up with here, or is there an assumption that China will do something different?
No, the development in China is factored into these things, and I think probably, I'm no economist, but I suspect some sort of middle path has been taken there. I must say I've been really heartened by what I've seen in China. There's obviously enormous economic development and enormous increase in energy use, but there is a realisation in the senior Chinese bureaucracy that this is a serious problem and needs to be dealt with. They've just introduced voluntary targets for emissions reductions, which will, if they're successful, see them reduce, I think, by about 15% over the next couple of decades. Be hard to believe, but this is what they're aiming at. But it's an extraordinary economy there. I mean, they're building nuclear power stations everywhere, damming every river in China, building the world's largest wind farm. It's quite an extraordinary series of developments.
When are we going to be forced to stop using fossil fuels simply because we're going to run out of them?
Well, I don't think that's going to happen. What we'll see is, as the price of oil rises, for example, we could go either one of 2 ways. The world is full of oil shale deposits and tar sands. Of course, using them has horrendous carbon implications. They're much more polluting than standard oil fields. But as the price rises, they become more and more competitive, cost-wise. So the oil companies will either go and start developing those resources, or else they'll start developing biofuels, because biofuels likewise become very cost-effective. If you look at Brazil now, I think 1/3 of the cars sold in Brazil last year approximately were dual-fuel vehicles, which can run off either ethanol or fossil fuels.
Is ethanol as polluting?
No, it's not, because, the thing about the carbon that's in the ground, in the fossil reserves, coal and oil, that's carbon that was last in circulation in the atmosphere hundreds of millions of years ago, when the atmospheric composition was different. There was dinosaurs around, or, in the Carboniferous, cockroaches grew to be 1 metre long. It was just a different atmosphere. That is, if you want, carbon that's been sequestered, for a very long time and very safely. Trees are built out of air, So this stuff here, they're not built out of the soil they come from. This is carbon coming straight out of the air. So when we use ethanol, that's carbon that was literally in circulation last year. So it's not the same as taking fossil fuels, which have been safely sequestered a long, long time, and releasing them into the atmosphere. Yes, sorry.
I wanted to ask you about feedback loops, and I saw that you mentioned one, with positive feedback loops, where the ice cap melts and the ocean absorbs more heat and and contributes to it. The only other one I've heard about is, from peat deposits in Siberia. Permafrost melts, more carbon dioxide released, and it contributes even more to it. You happen to mention that most feedback loops are positive rather than negative. Are there major examples other than
the soil carbon store? The decomposition rates in the soil are directly affected by temperature, so as soil temperatures increase, decomposition increases and CO2 releases increase. There's some very interesting studies done in Britain on those impacts, which show just how large scale they are globally. As atmospheric CO2 increases, it gets absorbed by the oceans and becomes carbonic acid, and the oceans acidify, and that then prevents the oceans from absorbing further CO2 because it affects marine life. So there are a number of positive feedback loops at the very large scale that scientists worry about in terms of these big, the potential for big emissions. Another very striking one that's probably as alarming as the shutdown of the Gulf Stream, but much more likely, is the collapse of the Amazon rainforests. And should that occur, the computer projections suggest that it'll be under real stress by about 2040 for a number of complex reasons. But should that collapse occur, we'll see CO2 levels at about 1,000 parts per million rather than 650 parts per million by the end of the century. So there's quite a number of very significant ones out there.
I'm curious, what do you think the biggest bang for the buck is in terms of fixing this? Is it solid state lighting? Is it population control? What's sort of there's of course 1,000 things we can do. What's the juiciest one?
The juiciest one is to get the polluter to pay, because once you do that, you put the other means of generating electricity or indeed transport fuels on an equal basis, equal footing. So in terms of the US, I mean, God, the free market here can do almost anything. It's an enormously powerful tool. If the US government decided to introduce a broad-based revenue-neutral carbon tax, so it's a carbon tax that goes right across the board, and being revenue-neutral, I mean you remove some other taxes, like some of the employment taxes and whatever, and replace that with a carbon tax, you would have a huge impact. You'd start seeing immediate changes. I really think that you would unleash a flood of innovation as people sought to find other means of generating transport fuels and electricity. So
carbon credit, is that a little bit different than what you're talking about?
Yeah, carbon credits, that's part of a cap and trade system, which the European Union has gone into in a big way. It allows you to, it's sort of, you can think of it as minting of a carbon dollar, really. It allows you to trade your carbon credits in a way that allows those who can reduce their emissions most easily to do so. The system, I think it's suboptimal compared with a carbon tax simply because it's more open to corruption and more difficult to enforce. And it's not so bad in the EU, but when you go beyond that to a larger group of trading partners, it becomes, I think, quite difficult to enforce. It's strange that the Kyoto Protocol, the initial discussions were premised on a carbon tax, but to accommodate the US, they took up this cap and trade model, which had worked very well with sulfur dioxide in the US. And so that's now the dominant paradigm. It would be ironic in a way if the US did introduce a carbon tax and got ahead of the game that way, which we'll see.
So you were talking about transport fuels. What's our best hope for the future? I mean, how does biomass scale?
Well, the US imports about $60 billion worth of oil per annum. Farm incomes in the US are worth about $65 billion. So I guess just thinking about it very simplistically, if I were a US farmer, I'd be looking at doubling my income by getting into the biofuels business. There's a lot of investment being made now in enzymes to create biofuels out of wood cellulose and some of the more difficult molecules. My suspicion is that biofuels are pretty much ripe, ready for the taking. You wouldn't want to use corn as a basis for it, but you could use other plant products. And certainly in Brazil, I mean, it's got a great future and will continue to have a great future. Now, Brazil's a wonderful place to grow plant matter, obviously. So, yes.
You mentioned all the negative consequences of the extra carbon dioxide. Does nature not respond? Does the extra carbon dioxide not create opportunities for new plants to soak it up?
Yeah, ultimately it does. And the thing, what is so damaging about this particular episode of climate change is it's very large scale and very quick. And we divide up the geological record into periods based on big extinction events, many of which have been caused by climate change. Everything that lives on the planet today is adapted to this climate. Should that climate change on a very large magnitude and very quickly, obviously nothing is adapted to the new conditions. There might be a few species that can fortuitously tolerate it, and they'll presumably be the species that in the next geological era will go along and proliferate and leave their descendants in great numbers. But that transition period is, we are moving away from a climate that everything's adapted to. Just in terms of our global civilization, I know you're not talking about that, but about species, but you can't pick up cities and move them, just like you can't pick up forests and move them. So they're adapted to the free services given to us by this climate, which are rainfall in particular areas and sea level at a certain level and protection from extreme weather events and what else. And as those services come to be withdrawn, then the systems are placed under greater stress.
The increase in average temperatures, what's the short answer for why an increase in average temperature by 2.5 degrees would be drastic? Is that, I guess it's compounded by the fact that it's over a short period of time, but otherwise, by itself, why is it?
Well, it's a sort of complex question to answer, but I'll try to do my best. The first thing is that this particular climate change is in a direction which will take the Earth out of the sort of envelope of past changes. We've just come through a rapid warming trend, as I said, 5 degrees over 7,000 years. We're now at the top of the warm cycle, So adding an extra 2.5 degrees to that takes us out of the, what the Earth has known for at least the last 3 million years. So that's one reason it's dangerous, because it's unprecedented in that sense. It's very, very quick. It's happening over a century rather than over thousands of years, or projected to. And it's also caused by an unusual set of forcing agents. It's not the Milankovitch cycles driving things, it's greenhouse gases, and they work in rather different ways. CO2 captures wavelengths of heat energy that are very long. They're most abundant, over the poles. At the same time, and of course they warm the Earth in the troposphere, And if you go to the next layer of the atmosphere, the stratosphere, what we're seeing is a marked cooling trend due to the reduction in ozone. Ozone used to protect us by capturing sunlight and turning it into heat energy in the stratosphere. That's no longer happening. So I would say, those things at speed, really the fact that we're going out of the envelope of past climate change, and the fact that this forcing agent has different consequences from the celestial cycles, all I think add to the potential danger of this particular climate shift. Yes, one more.
Are there any efforts to try and use bioengineering to suck out some of the atmospheric carbon dioxide released?
There's been a number of experiments to do that, and you're quite right to ask that, because increasingly people are beginning to feel that we have either reached that tipping point or perhaps are beyond it in terms of the potential to allow these positive feedback loops to run away. Probably the most, long-term experiments have been the ocean fertilisation experiments in the Southern Ocean, where people have taken great big freighters full of iron filings and dumped them into the Southern Ocean in the hope of simulating plankton blooms that will capture carbon and sink to the seafloor. They stimulated some wonderful plankton blooms, but the plankton didn't sink as it died. It floated and rotted at the surface and re-released the carbon. So those experiments are at an end. Direct sequestration in the ocean was another attempt, where people tried to pump liquid CO2 into the ocean depths. It proved to be so catastrophic to ocean life that the experiments have been discontinued. The real impacts that we're going to see is probably on the soil carbon store and the living carbon store on land. But those experiments have to be very broad acre in their approach. Just to give you a general idea, to reduce CO2 levels by 1 part per million in the atmosphere, we need to sequester about 15 gigatons of carbon in living sources, plants and whatever else, or in the soil. At the moment, the regrowing forests of the USA that were cut back during the pioneer phase and now growing, they pull about 1.5 gigatons of carbon out of the atmosphere a year. So you get a sense of the scale of those required experiments.
Well, so if you see this global warming event, won't we see, with increased rainfall, will we see increased vegetation in some of the desert climates, which would in turn pull more carbon out of the air and in effect kind of check itself?
So a negative feedback loop.
Right.
That was what was originally thought, that was based on CO2 fertilisation, that CO2 helps plants grow faster. It turns out that the response of plants in the real world is much more complicated than that. Only some plants respond optimally to CO2 fertilisation, particularly the C3 woody plants. The C4 cycle plants, like the crop plants that we use, wheat and rice, don't respond as strongly. But also you have to remember, extreme weather events, decreasing soil moisture due to higher evaporation rates, other changes that make it difficult for plants to grow as quickly as they were before. So it's uncertain as to which way things will go. Certainly some plants in the tropics are already growing faster, but the overall impact is hard. And of course the other thing you have to remember is albedo. As we grow forests in areas that were once snow-covered tundra for part of the year, those dark forest canopies capture heat energy rather than reflecting it into space. So there's so many complexities, it's very difficult to tell how the whole thing is going to play out in terms of whether it'll be a positive or a negative feedback loop with vegetation.
Is there a chance of a phase shift that would snap us into a colder cycle?
Well, certainly the Gulf Stream will cool down part of the planet, will cool down Europe and North America. That's one of the few negative feedback loops in the system. But you have to remember that heat that was once transferred north by the Gulf Stream doesn't just vanish. It's got to go somewhere. It'll pool around the equator or into the southern hemisphere where it'll cause further changes. So, ultimately we may be faced with a cooling planet. Just say we get on top of this problem and we reduce our emissions, in 3 or 4 centuries' time we may be faced with precipitous declines in temperature as those celestial cycles start reasserting themselves. And that's when you really would want to have some coal deposits to burn to get you out of it. I suggest in the book, the first person to realise this was Arthur C. Clarke, and I suggest in the book that we should set up an Arthur C. Clarke fund for for fighting the Ice Age and get nations to contribute to buying up coal deposits around the world so that they'll be there when we really do need them in a few centuries' time. But, yeah. I think I should probably... All right, thank you.